Our next presenter is Dr. Dandina Rao, joined Louisiana State University and is currently a distinguished professor in the Craft and Hawkins Department of Petroleum Engineering. He has been involved in rock fluids interactions and enhanced oil recovery research and field project implementation since 1983. In addition to developing the gas-assisted gravity drainage process for enhanced oil recovery, Dr. Rao has invented the hydroflame process for direct contact steam generation for heavy oil and bitumen recovery and for flue gas generation for conventional light oil recovery. The dual drop, dual crystal technique for confident reservoir wettability characterization, and the vanishing interface technique for quick and cost-effective gas-oil miscibility determination. Dr. Rao holds a B.Tech with distinction from India, a master's degree from the University of Saskatchewan, Canada, and a PhD from the University of Calgary, Canada. He holds several patents in the US and in other countries, in addition to publishing over 125 technical papers. Recently, in 2019, Dr. Rao was elected a senior member of the US National Academy of Inventors. Dr. Rao will present to us the role of wettability alteration in low-salinity water flooding USA. Remember to leave your comments and questions on the chat. They are going to be discussed on the panel section. Thank you, Dr. Rao, for being here with us today.
Hello everyone, I am Dandina Rao. I'm a professor of petroleum engineering at Louisiana State University, Baton Rouge, Louisiana in the US. My research associate and my co-author on this paper is Dr. Bikash Saikia. We would like to thank the organizers of this meeting, this symposium on EOR for IEA, for giving us this opportunity to present our research results. The title of my talk is The Role of Wettability Alteration in Low Salinity Water Flooding. Low salinity water flooding has received significant attention, as we can see from the number of papers. Back in 2010, we were looking at 25-30 papers, and in 2019, as you can see, this is over 750 papers in 2019. So there is a significant interest in this area by the industry, and that's because we can avoid extensive investments associated with conventional EOR methods, and the payback is also faster even if the incremental oil recoveries are small. And the number of papers we discussed very clearly indicate the industry's interest in this. And the snapshot of low salinity research, there is significant progress in this area, and I've listed a few things here. On sandstone reservoirs, they've observed significant improvements in oil recovery, and also in carbonate reservoirs, although they're a little more complex because of the fractured nature and unfavorable wetting, initial wetting states, and so on. And the ionic composition of the injected brine and the reservoir temperature also are shown in our work and in other studies to have an influence on the amount of oil we can get out by this process of low salinity water flooding. So wettability alteration appears to be one of the main reasons in enhancing oil recovery by low salinity flooding. And also we found very interestingly, like some of the other researchers also have found this, that sulfate ion in the presence of calcium and magnesium has a significant wettability effect alteration and on oil recovery in carbonate reservoirs, and we'll show some of the results to substantiate all these statements. And increasing the temperature makes the carbonate system to shift towards more water-wet state. That's also been debated in the literature, but we have some good experimental evidence to make this point in this presentation. And although all these observations have been made, the clear understanding of this still seems to be elusive. From a mechanistic point of view, we are still looking for answers. Wettability, a quick definition of wettability is needed because there are so many of them out there. It's a general definition is tendency of one fluid to spread or adhere to a solid surface in the presence of another immiscible fluid. And there's more to it than what this sentence says, and we'll talk as we go along about this. And the importance of wettability is that it influences the very fluid distribution in the reservoir, where oil is located, where is water on the pore network of the reservoir rocks. So the fluid distribution, and it also affects the effectiveness of all recovery methods we adopt in these reservoirs. So for those two very good reasons, wettability gets a lot of important attention, truly deserving attention. In general, if the water advancing contact angle, which we will define in a minute, is what really characterizes the wettability, uniform state of wettabilities. Water wet, we consider the water advancing contact angle to be in the range of 0 to 60 degrees. 60 to 120 degrees would characterize the system as intermediately wet, and anything beyond 120 would be called oil wet. And wettability alteration really means overcoming the strong rock oil adhesion interactions. And I have a 1 minute long video to make that point. And of course, relative permeabilities. But through corefloods, we can determine the ability of the porous media to conduct one fluid in the presence of two or more fluids. And that relative permeability parameter, which is so important for us in our business, also depends on wettability. So these are the points that we will discuss. The objectives of this work done by one of the master students here a few years ago, was to investigate the effect of brine salinity, brine composition, and temperature on wettability. I'll try to present all these aspects and determine also in the process optimal brine composition and optimum salinity for enhancing oil recovery, and that's through corefloods. And also explore the experimental data we collected in relation to the published literature to understand the mechanisms behind such wettability alterations. Methodology-wise, we used what's called a dual drop, dual crystal technique for measuring water advancing and receding contact angles. I will present briefly what this technique is in the next 2 slides or so to describe it for you. And the recovery factor determination, of course, comes from corefloods. And what we have used is Silurian dolomite in place of Yates reservoir rock. All our work in the previous years has been done with Yates reservoir, which is a prolific reservoir in West Texas. We got the rocks and fluids from that formation. Oil is the Yates crude oil, and the reservoir conditions are quite easy to handle, 700 psi and 82 degree Fahrenheit. And brine, of course, we made up the brine, synthetic brine, that matches the composition of Yates reservoir brine. And corefloods, of course, we do the brine flood to determine the pore volume, absolute permeability, and the oil flood then to drive the core to initial water saturation and endpoint oil permeability measurements. And water flood is then conducted with various brine compositions and salinities. And that water floods will give us the results on recovery, endpoint, relative permeability to water, and so on to complete the story of relative permeability plotting. So the relative permeability determination is done through simulation, core flood simulators, and of course further data analysis and interpretation to decipher wettability effects from these relative permeability curves we generated with varying compositions and brine salinities. This is the dual drop, dual crystal technique. Uh, as the name sounds, dual drop, dual crystal, two drops on two crystals, and that's what we start off the experiment with, and you'll see why we do that in a little bit. And next, after aging these two drops on these two crystals overnight, we flip the lower crystal upside down, and three things can happen. If the oil rock adhesion here is strong enough, you will see that all the oil drop is retained on the lower crystal. If the strong adhesion is weak, some part of the drop will stick to the lower crystal and most of it will float away due to buoyancy. And if the adhesion is even weaker, all of the drop will go away. In the next step, what we do is to bring down the top crystal down onto the lower crystal, towards the lower crystal, so that we mingle these two drops, this and this. And in this particular case, we try to bring it to the area where there was oil drop before, that same area there. And that's so important. And you'll see that in a minute. So once we do that, mingling of the drops, then we pull the lower crystal to the sideways, they shift it from outside. And these cells are high pressure cells operated at 20,000 psi and 400 degrees Fahrenheit. Those are the limits. And I'll show you the videos where we did some high pressure, high temperature work after this slide. So these, when we pull the lower crystal to the side, the drop, in its effort to get back to the equilibrium shape, it moves in this direction, and that allows the water here, the blue is water, these are crystals, either quartz or calcite or what have you, and when the drop moves, water here or brine advances over a previously oil occupied area that I'm showing here in this part. So that meets the definition. The very definition of water advancing contact angle is that the water advances over a previously oil occupied area. Only then, when it is moving and it is in the previously oil occupied area, the water oil interface, the angle measured here meets the exact definition of water advancing contact angle. And that's where the weakness has been in the literature, some of the measurements we made also in the early stages were not meeting those definitions, and that's why there is a lack of reproducibility in the contact angle literature, quite a bit of that actually, and that has led to some skepticism as well as some confusion about this. And we have written other papers to, as much as possible, to clarify these aspects. So if anybody is interested, please reach out to me through my email address at dnrao@lsu.edu. I'll be happy to share those papers with you. This is the high pressure optical cell that we have here at LSU. This is the one that supplies the hot air to heat the box surrounding this cell. There's a camera system. There is a prism that deflects the part of the image to the goniometer here, and part comes right through to a recording camera, and there is a light source at the back here. And the pressures, of course, pumps and compressors are used to pressurize the system. We can go up to, in this cell is particularly designed for 20,000 psi and 400 degrees F. Here is the 1-minute video on the 3 different wettability cases. The first one is water wet case. These are the oils on quartz crystal, Beaver Hill Lake fluids on quartz crystal, and the reservoir conditions were 24 MPa and 96 C. It starts off with 2 different drops placed on 2 crystals, and then the bottom one was rotated and the drop flew away because very little adhesion force. And then we mingled the 2 drops, as you saw, and pulled it to get the contact angles. I'll show you the results of. Here are the 2 drops again for the intermediately wet case at different pressures and temperatures. As we turn the crystal sideways, and you can see the drop could have gone, but it does eventually, but still leaves some oil behind because there is some adhesion force that has developed within the same time overnight. And then we mingle the 2 drops and pull the lower crystal to the sideways to make that angle of 108 degrees or so. That's what qualifies as intermediate wettability. This is the very first case, but that was quartz in the first case. This is calcite, and you can see most of the oil drop stayed. In fact, all of it stayed, and it would rather have a cohesive failure than a movement on the lower crystal surface, and that's because the adhesion forces are so strong. So what were the angles in these three cases? And that's what is shown here. You see that the 4 different times we measured for the water wet case, the very first case on quartz crystal, the 50, 53, 52, 50, very highly reproducible. That's why I call it a reproducible technique. That's what this is. Whereas the conventional technique of pen and drop measurements would give you 40 degrees, somewhat misleading. In the intermediate wet case, it's a different reservoir fluid and different reservoir pressures and temperatures. And again, the 4 readings are very close to each other, 108 to 110 degree range. And the oil wet case, that was the same reservoir as this, but we, instead of quartz crystals here, we used calcite crystals. You see a world of difference here, 144 to 147 degrees. Plus or minus 2 degrees is the reproducibility of this technique. And whereas if you had measured the same oil, same crystals, same conditions, you would have gotten 25 degrees from pen and drop technique, indicating this to be a water wet case, whereas in fact it is extremely oil wet. So that is the difference between this technique and the conventional ones that we had been using before. So that's why we have used this technique in this study also. Here is what we did in this study in terms of salinity variation and the water advancing contact angles at ambient conditions. Here is the Yates brine composition, and these are the components in the brine, and the twice diluted, 10 times diluted, 50 times diluted, and 100 times diluted. These are the cases you will see in the results slide next. And Yates reservoir brine itself, as we said, it is strongly oil wet. That was the angle, 158, and these pictures are taken from those videos of each one of these experiments. And then when we did the twice the volume of the same brine, twice diluted, and that gives you about 150, slight reduction there, but not much, still oil wet. And 10 times dilution yielded some more reduction in the advancing contact angle, but still in the oil wet range. But then when we diluted it 50 times, the Yates brine, when we diluted 50 times the original concentrations, then it yielded an intermediate contact angle of 113 degrees. And this we will see in the coreflood results also having an impact on recovery. But when we went up to 100 times dilution, the angle showed a slight increase, but very close to the border of intermediate and weakly oil wet region. About 120 was the limit. It's about 125, just over the limit of intermediate wettability. And we also did the composition variation, and what we did was Yates synthetic brine composition is here, and the total dissolved solids was kept constant throughout, 10.7 grams per liter, but we varied this. There was no sodium sulfate. We wanted to try the sulfate concentration effects here, and we added some sulfate here in test 1. Test 2 did not. Test 2 was just the same original brine here. And test 1, we had 2.2. That all those sodium sulfate came from NaCl concentration. This went down. And then when we added 1.1, 4.4, double that, half this, and double that, and so on. And in the last case, test 5, we took out all the salts and only added 10.7 grams per liter of Na2SO4. And these are the test identities that you will see in the next slide here showing the results. Test 1. So 158 original reservoir brine, 154 and so on, and test 4 and test 5 again, it goes back, a similar effect that you saw in the past. Here, and you will see here the salinity variation and water advancing contact angle. The salinity variation was this, as I said, up to 100 times dilution, 50 times. And the second case was brine with 4.4 grams of sulfate ion concentration. And here we see all the results here. Reservoir condition, ambient condition in red, reservoir condition in blue, and green at high temperature, 250 F. And we see that at ambient and reservoir conditions, the results are pretty close to each other, 122, 125, and so on. But 50 times dilution, of course, showed a significant reduction in the contact angle, 157 to 112 degrees. And something similar happened with the 4.4 gram per liter sulfate brine, also very close to this initial conditions. At high temperature conditions, however, the contact angles in every case is less than the room or ambient reservoir condition or ambient condition ambient temperatures. And that is well known in carbonate systems. We have other publications that show more results of this type for better clarity. So here are the results from core flood experiments. Several core floods we did. Again, we picked the optimum cases from the previous contact angle results. H brine with 4.5 gram per liter sulfate concentration, and 50 times diluted brine. H brine 50 times diluted here. And the salinities were the same here. This one, of course, went down 50 times. So recovery factors, 46% to 74% to 76%. So these two seem to be 50 times dilution of H brine seem to be very close to what a brine with 4.4 gram per liter sulfate can do in many cases. And these are the saturations and endpoint relative permeabilities. And here is the simulation results. We kept all the endpoints the same to get the relative permeabilities through a core flood simulator that we used. Here the experimental data are shown shown by points, and the calculated simulated data is in the lines here. You can see we get an excellent history match of the recovery factor as well as pressure drop. And when the matches are good, we accept the relative permeability curves as being good. And this is what we did for all the core floods. And the results are shown here in terms of recovery here. The synthetic reservoir brine itself had about 45% or so, 46%. And here is the 50 times diluted brine is the red, and the green line is for brine with sulfate brine, let's call it. And they're pretty close here, about 76% or so. And so it's quite a bit of an improvement by both these techniques of diluting the brine as well as sulfate brine. And the relative permeability curves are actually plotted here as the ratio of KRW or KRO, and that's because the shift to the right indicates a definite shift in wettability towards intermediate wet, water wet situation. And by the contact angles, we can precisely say that the shift was towards intermediate wettability. And we know we have from our own lab and other labs, there are enough publications to indicate that oil recoveries are optimum in the intermediately wet state, better than even water wet state. So that's this kind of confirmed the same results as in the past as well. So these are the same results, salinity variation and the advancing angles shown here, and the recovery factors. It's just a summary slide of all the results I have discussed so far. In terms of mechanism, we were trying to relate the pH of the brine with respect to the isoelectric point of the rock surface that we have been using in our experiments, which is dolomite. And dolomite IEP, isoelectric point, is around 8.5 pH value. And at that 8.5 pH value, there is evidence that the water film collapses and the oil contacts the rock and becomes oil wet. As you move away from it in either direction, then the wettability shifts towards intermediate wet or less oil wet, so to speak. And that's what we see here in this case, and the literature evidence is also showing the isoelectric points of alumina here and gold here and so on. They make also a similar argument, and our results also seem to support that. Here are the conclusions from our study. The measured water advancing contact angles 158 and 157, very reproducible at reservoir conditions. The H reservoir indicates very clearly strongly oil wet nature of this formation. Significant wettability alteration from strongly oil wet to intermediate wet was observed with 50 times diluted brine at both ambient and reservoir conditions. So brine containing 4.4 gram per liter sulfate in the presence of calcium and magnesium cations has the most significant impact on changing the wettability to bring the system from strongly oil wet to intermediate wet. That was a new finding for us. And after this study was reported in an SBE paper, there are several papers that have appeared on the examining the effect of sulfate ion concentration on low sal flooding. The effect of temperature on wettability was significant, as we showed here at 250 degrees. Because we tried that because this reservoir was steam flooding was being considered for this formation, and that's why we tried to give them some data on that. The company was working on that reservoir at the time. Core floods conducted with 4.4 gram per liter sulfate and 50 times diluted brine both gave higher oil recoveries than undiluted H brine, as we showed. And the potential mechanism seems to be related to the isoelectric point of the rock minerals used. And well, I thank you for your attention. And if you have any questions, I'll be more than happy to answer if you could email them to me. Thank you so much and have a nice day.